What if one of the most powerful forces shaping the universe is something we cannot see at all? From the Earth's poles to the Milky Way's spiraling arms, magnetism has guided migrations, powered technologies, protected life, and even shaped the evolution of entire planets. To understand magnetism, we must follow a trail that begins in the ancient world, passes through medieval lodestones, enters the laboratories of Renaissance experimenters, and stretches forward to the particle accelerators and space probes of today. This is the real history of magnetism, defined by precise measurements, tested theories, and discoveries that continue to change how we understand the cosmos. Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today, we journey into the story of magnetism, where ancient observations, modern physics, and the hidden architecture of reality collide. The story begins in the region of Magnesia in ancient Greece, around the 8th century BCE. Early Greek shepherds and metalworkers discovered naturally magnetized iron ore known as lodestone. These stones attracted small pieces of iron and puzzled ancient observers. By the 4th century BCE, Aristotle recorded references to magnetism influenced by the works of his teacher Plato. Although their explanations were philosophical rather than scientific, these early observations marked the origin of a concept that would shape human civilization. Magnetism gained practical importance in China by the 2nd century BCE during the Han dynasty. Archaeologists discovered magnetic spoon-shaped compasses made of lodestone, excavated from burial sites dated between 206 BCE and 220 CE. The earliest written reference to magnetic direction finding appears in the Chinese text The Book of the Devil Valley Master, written around the 4th century BCE and later expanded during the 3rd century BCE. By the 11th century CE, Chinese navigators of the Song dynasty used floating compasses to guide maritime expeditions in the South China Sea and the Indian Ocean. Meanwhile, in Europe, knowledge of magnetism expanded slowly. During the 1st century CE, the Roman author Pliny the Elder described lodestones in his encyclopedic work, Naturalis Historia. Although he lacked a scientific model, his descriptions provided valuable records of early Western encounters with magnetic materials. The scientific revolution transformed magnetism from a curiosity into a measurable phenomenon. The major turning point came in 1600, when the English physician and natural philosopher William Gilbert published De Magnete. Working in London, Gilbert conducted detailed experiments on lodestones and iron spheres. He concluded that Earth behaves like a giant magnet with north and south poles. This was a groundbreaking idea, supported by his observations of compass needles and their interactions with spherical magnets known as terrellers. Gilbert's work marked the birth of terrestrial magnetism as a formal scientific field. In 1750, Benjamin Franklin in Philadelphia began investigating the relationship between electricity and magnetic behavior. Franklin proposed that lightning was electrical in nature. Although he did not yet connect electricity and magnetism directly, his work opened the path toward a unified understanding of electrical forces. The 19th century became the most transformative period in the history of magnetism. In 1820, the Danish physicist Hans Christian Ørsted performed one of science's most important demonstrations at the University of Copenhagen. While lecturing, he noticed that an electric current passing through a wire caused a nearby compass needle to deflect. This was the first recorded observation showing that electricity produces magnetic effects. Only months later, French physicist André-Marie Ampère expanded Ørsted's discovery. Working in Paris, Ampère formulated mathematical laws describing how electric currents interact. His findings laid the foundation for the field of electrodynamics and inspired further experimentation. In 1831, the English scientist Michael Faraday extended the connection between electricity and magnetism by discovering electromagnetic induction. At the Royal Institution in London, Faraday demonstrated that moving a magnet through a coil of wire generates an electric current. This principle powers nearly every modern generator and transformer. Faraday's experiments introduced the concept of magnetic fields as regions where forces act, although he described them visually rather than mathematically. James Clerk Maxwell provided the next major breakthrough. Between 1861 and 1865, while working in London and later Cambridge, Maxwell published a series of equations that unified electricity, magnetism, and light. His equations predicted that electromagnetic waves propagate through space at a finite speed. This speed matched measured values of the speed of light. Maxwell's insight revealed that light itself is an electromagnetic phenomenon. As the 20th century began, magnetism entered the realm of atomic physics. In 1922, Otto Stern and Walter Gerlach conducted their famous experiment in Frankfurt. They passed a beam of silver atoms through a non-uniform magnetic field and observed that the beam split into two discrete directions. This demonstrated that atomic properties called spin generate quantized magnetic moments. The Stern-Gerlach experiment was one of the earliest experimental confirmations of quantum mechanics. In 1928, physicist Paul Dirac proposed the Dirac equation while working at the University of Cambridge. This mathematical formulation predicted the existence of antimatter and described the behavior of electrons, including their magnetic properties. Dirac's model reinforced the quantum origin of magnetism at the particle level. During the mid-20th century, laboratories in the United States, Germany, and the Soviet Union studied the magnetic behavior of ferromagnetic materials like iron, cobalt, and nickel. Researchers such as Louis Néel in France and Charles Kittel in the United States clarified how atomic spins align to form magnetic domains. In 1970, Louis Néel received the Nobel Prize in Physics for his theories of antiferromagnetism and ferrimagnetism. Space exploration added a new factual layer. In 1958, following the launch of the Explorer 1 satellite from Cape Canaveral, American scientists James Van Allen and his team detected radiation belts trapped within Earth's magnetic field. These belts, now known as the Van Allen belts, provided direct evidence that Earth's magnetosphere protects the planet from charged solar particles. Subsequent missions, including NASA's Voyager probes launched in 1977 and the European Space Agency's Cluster mission launched in 2000, mapped magnetic structures around Earth, Jupiter, and Saturn. Verified geological discoveries also deepened our understanding of historical magnetism. Beginning in the 1950s, geophysicists studying mid-ocean ridges found symmetrical magnetic patterns in seafloor basalt. These patterns preserved ancient magnetic reversals. The work of Vine and Matthews in 1963 linked these magnetic signatures to the theory of plate tectonics. Modern magnetism is a field defined by precision measurement and advanced technology. Particle accelerators, such as CERN's Large Hadron Collider in Switzerland, use superconducting magnets to bend the paths of protons traveling at near light speeds. These magnets operate at extremely low temperatures maintained by liquid helium, and are among the strongest and most stable magnets ever engineered. Researchers today study magnetism at the quantum scale. In 2008, scientists at the University of California, Berkeley, imaged magnetic vortices inside superconductors using a scanning tunneling microscope. In 2019, researchers at MIT identified a new class of magnetic materials called twistronics, in which graphene layers rotated at specific angles exhibit superconductivity and novel magnetic effects. Magnetism also extends beyond Earth. Spacecraft such as the Juno mission, launched in 2011, have mapped the magnetic field of Jupiter, including its polar auroras. In 2016, NASA's MAVEN probe measured how changes in the solar wind eroded the ancient magnetic field of Mars. These findings help explain how Mars lost much of its atmosphere and water over billions of years. Present-day applications of magnetism include magnetic resonance. Imaging, developed in the 1970s by Paul Lauterbur and Peter Mansfield. These machines measure nuclear magnetic behavior inside human tissues to create detailed internal images. Hard drives rely on magnetic domains to store digital information. Maglev trains operating in Japan, China, and South Korea use magnetic repulsion to achieve frictionless movement. The underlying theory of magnetism is now firmly established. Magnetic forces arise from two sources. The first is the motion of electric charges. The second is intrinsic spin, which is a quantum mechanical property of particles like electrons. All mainstream scientific explanations of magnetism rely on these principles. Any alternatives that attempt to explain magnetism without charge motion or quantum spin are classified as speculative hypotheses rather than validated theories. Magnetism is one of the most ancient forces known to humanity. We have used it to navigate oceans, build machines, explore planets, and uncover the laws of physics. It is also one of the most revealing forces. Through magnetism, scientists discovered electromagnetic waves, the structure of atoms, the behavior of quantum particles, and the protective systems that shield Earth from cosmic radiation. From lodestones found in ancient Greek soil to superconductors developed in 21st century laboratories, magnetism has guided our understanding of nature at every scale. Its history reflects the development of science itself. Careful observation led to experimentation. Experimentation led to mathematical theory. Mathematical theory led to technologies that reshaped the world. The story of magnetism is not a tale of mystery. It is a story of evidence, measurement, and discovery across thousands of years and across continents from China to Greece, England to Germany, and Earth to the outer planets. The hidden forces of magnetism have always been with us. As we uncover their secrets, we reveal the structure of our world and the deeper workings of the universe. This is Mattermosaic, piecing together the universe, one discovery at a time. If this journey into magnetism sparked new curiosity, tap like, share it with someone who loves science, and tell us what idea you want explored next. Be sure to subscribe for more weekly explorations, and keep watching to discover the next story waiting in the fabric of reality.